Let me turn on the audio here.
Can you now see my terminal window on my Linux box?
Yes.
Hello?
Has joined the meeting.
Hold on a second here.
I'm still here.
Line, but there seemed to be, I thought I was causing that back.
I'm recording, but I'm not sure about audio.
Record the audio. If it says it's recording, it's good.
Do we have everybody online that needs to attend?
Has joined the meeting.
Is that Keith?
That's quiet, I guess.
Was in.
Hi, Tom.
Ayun. Is Pon there with you?
No, I think he's going to join in the meeting.
So waiting for Pon and I think Keith. I don't know, Bob Berger, was he going to join?
In an invite, I am not sure. Let me check with Victoria. Oh, Michelle, while we're waiting, do you mind if we go through the action items?
No, go ahead. Mm-hmm.
Okay, so I'm looking at the our emails. We traded email earlier.
Yeah.
So got that for.
Yeah.
Yeah, and share my screen first.
Actually, I had it just here.
Oh, I'm sorry. You're showing your okay. Let me make you a
Oh,
present.
that's fine. Or it doesn't matter.
We need to share the screen again. I'm sorry.
Oh, that's fine. That's fine. Okay.
No.
So, pardon me?
Your screen now.
Okay, good. So this I got from you a few minutes ago. So item 1 was to send the training on the gateway. So that was done, I believe. Is the audio and recording okay? I think you had some user actually going through after that, right?
you the recording, and it was perfect.
Good. Item 2 was the list of redundant services.
Has joined the meeting.
But
So whenever you're ready.
Hamilton is on vacation, so I don't know the status.
That's, you're up and running. It's more of a safety feature that would help you if would go down or something, but as long as it stays up. And if worst case, if that was to happen and you need to quickly remap everything to another temporary machine, we could always cut your license within a few hours. So, but that's a safety approach, so that's good. The list of DCEL and IOCEL, I got some shared with me some stuff. I got some feedback from the PDK groups. I need to pass that along to you as far as timing. They may need a sort of a priority list on which PDK to hit first, but I'll share that with you following our meeting today.
Has joined the meeting.
I sent you a list of processes we have been using now. XDH10, XDH10, CHO8. When we were looking at the list, there are so many and different flavor. I don't know where to start. I can send you a list of their, web book, but it doesn't do much. So if the K group can at least get a short version of it, include IOCEL, because right now I don't see any IOCELs in any of the PDK, and also not just for gateway, for for backend as well.
Work will basically include having the symbol, the CDL netlist or whatever comes with that IO or digital cell. Them netlist properly so that they can drive the backend standard cell for that IO or digital cell. So they place and they have the NDL port so you can drive your layout from that schematic netlist.
Right. That would be perfect.
That's what
you mentioned trace and route. So if you are using Spider, you definitely need the better LEF lip cells and Verilog. So if the PDK group can accomplish a short list, and then I think we can make the list as we go along with the design.
I think that these not to actually create the list of cell and provide it. Is that for them they can't hit every process at the same time, so they would need some info from you on, okay, out of this list of PDK, which one do you want us to work on first, right? If it doesn't really matter at this point, I'll just hit one after another and provide them when you can. But if you say, I want to look at this first, then,
Can we talk about the list right now? Because I would say XDM10, XDH10, then XT06, and CX08. The two versions of CX08 is, A version and HV version. So we need both.
Yeah.
And then the last one is XC06. Those are the processes we are using right now. And after that, the PDK group can prioritize, whichever process they feel comfortable.
David, I'd recommend you give them the list and your priority.
I was talking about the list of the priority. We do XDH10, XDM10, and then XT06, then CX08A, CX08H, and XC06. And
Okay.
Can be any order.
Okay. So the first one would be the XDH10, then M, correct?
Yes.
Okay. Yeah, I'll provide that to them, and then we can give you a breakdown, a roughly estimate of when that would be available to you. Yep. Yep. Take a note to look for left equivalent of the cell and include that as well, if at all possible. Left equivalent to include. Okay. Down. Alrighty. Also, that was for point number 3. Point number 4, that's on me. Basically, okay, yeah. So was that the EDA summit? 3 days I was in California. I had a chance to talk to one other EE that is his job is to support gateway only. That's all he does. He's really good at it, and he has quite a bit of script written around gateway. So he will share with me a lot of those scripts, and I'll see what could be to actually those tasks and provide that to you. But I didn't get to that yet, so that's still pending. But I'm
Script?
just script actually.
Oh, just.
Any scripting or expert or gay is Java. Our PCL in older PDK were written into Lisa, which was really kind of a proprietary language, but we moved away from that. Now they're in JavaScript.
Perfect.
Yep. And then number 5, which was the print of hierarchical link. I didn't get any reply yet from development on this. I need to follow up. They have, get about it, but I didn't get any reply. So that's on me. I will double check on that. And the last point was basically providing all the necessary file for the demo circuit. And I think you did provide everything. So I think we're set to go on this. Question at the bottom, Gateway 200 and Expert 200. I don't use those for viewing purposes. They were meant to be used for kind of a cheap version of the tool, which has kind of a device limit. So they were cheaper to buy, if you bought a license, but it was more a pay-per-use format at that point. I don't think we even have that licensing scheme anymore. But I would use the gateway views and expert views, which come basically, it's expert minus view or gateway minus view. It opened that exact same GUI in view mode, just read only. So that should work just fine.
Is that something we need to install?
No, if you have gateway install, you could just basically make a copy of that shortcut, rename it like say gateway view, and you just put the switch minus view at the end, and then it'll launch it in view mode only. I'll provide you the detail on this, an email or something on how I would set it up, so that's not going to be a problem.
Okay.
I did not look at the license file in detail. I don't know if you have gateway views license per se. If not, you usually could certainly work setting up with Peter to have you of those. You have Charles. That's his fault, but we've done that with other customers. So.
Okay.
I will email. Yeah.
I will email to Peter.
him to check. Maybe it's going to reply it's already included. Like I said, I didn't look in the license file. You may already have some of those seed in the license file. I don't know. I didn't check. The other point was the OA or EDIF method. EDIF method, you can certainly have that capability. Access, this will be in our new baseline release, soon be released. So our date was July 1st. We went past that, so I'm expecting the end of this month for that release to come out for our baseline 2016. And this is the version that had all the open access work done on both Gateway and Expert. With your version of Gateway and Expert, you will not be able to test that out, but as soon as the version comes out, I can share that with you, and then you could play with that feature.
Great.
Still pending, in other words. That thing for the action, correct?
Correct.
Okay. So if no, we can start looking at InVar today. I was everybody was made aware, but we kind of, well, I kind of forced that on you guys because let's me be honest here. InVar is a company, or came from a company acquired about a year ago. So part of the acquisition, we acquired a development team, 4 developer or 5 developer, and they're mainly that knows that tool in and out. As far as me, I don't know it in and out yet. I'm still kind of in the progress of learning this tool, so there may be some that I'm not really familiar with the tool at this point, but I want to assure you that I do have access to it. He helped me basically every time to demo this tool, so I do have he's a phone call away, so that's not an issue. And if need be at any point where I can't resolve the issue, it's no big deal to get him on a deck or on the line with you guys because he's sitting in Santa Clara, so he's here in California, so that's not an issue. All right. It does basically IR drop. It does terminal analysis, power analysis, and vector migration. And we have basically kind of 2 ways of running it. We can run it into kind of a transient mode where it's going to run. You'll see progress as the simulation runs. You can see what's happening on the circuit. And you can run it also kind of a static mode where it would show you the worst case or the warmest point across the whole simulation, or the highest power consumption across the whole simulation. So it's more of a snapshot of worst situation, basically. So as far as the installation, I just want to go over that real quick. So for me, here, you all see my screen fine?
Yep.
So from here, I have my build Silvaco lib, and under the InVar folder, I have a few versions. Let me click here. There we go. So now, one reason why I had to basically spend more time to get ready for this demo is that they changed the GUI quite a bit. So now the 1.10.1 didn't really fit my knowledge of the tool, so I had to pair. So that's basically, and into there's some examples that are provided basically into the folder. So that's just the installation folder. Now, if we look at what's included as far as hold on, let me check this one. That's another one I want to look at. I want to look at the analog, and then, okay. Let's first look, and there's kind of a tickle script that sets up the flow. So let's first go through that, and you'll see the different section and what's important to have, and then we can, when I went through all of this, we can start and play with the tool. So I brought up here that flow, that transient. Close this one up. Okay, here we go. So I would launch InVar and point this statistical script, basically. And what it does, it will go and import the GDS of that design and layer map. That's basically show you that layer map. If I go into the GDS here, it just maps the OA layer name, the drawing layer, the GDS number, the purpose, and the material that is made of, and the number, which time is different. For example, 2 is 1, and so it's not necessarily a match one-on-one, but the map is actually important to have when you're in the GDS. Then you can look, the next section is basically importing the ITF data from the Foundry. So if we just look at that real quick into the ITF. Basically, this is a really basic ITF file, but this is basically the global temperature I'm going to work on, the dielectric, their thickness, their ER, minimum space, minimum width of the inductor, the resistance per square, their coefficient of temperature, and all of this. So kind of a cross-section slash thermal information that will be required when doing the analysis. I'm sure you have something similar in the XTO6, I want to say ITF. Then you have the EM rule for electromigration. So if we go and open that, it's specifying for each layer their current density maximum and all kind of stuff. So also information that could be provided by Foundry. Specified that we're going to do a design type analog, and we read the bias netlist. This bias netlist here fits more as the input deck that is actually provided to SmartSpice. So it could be a .in just as well as a .sp. If we take a quick look at this file here, say basic, include model, include the DSPF file that goes along with this circuit, stimulus, the type simulation I'm going to be doing, and it reads the device location and the DSPF, basically, the parasitic layer map that needs to be provided as well, part of the setup. Real quick, that's pretty straightforward. It's spice, parasitic spice, parasitic layer map. Typically, they'll have sometime a different name between the SPF and the layer. So there's a mapping that takes place here. Make sure that everybody understands each other. About it there. Then we set the design as that circuit, the SDFFRS. Then we need to specify our power net and their voltage. So basically we come and say create power net, it's a VDD, the voltage is 1.1, create ground net is VSS, it knows it to be 0, so we don't have to specify it. And we say we want to create a transient analysis, and this is the end of the kind of thing that we just created here, that section here, right? And then we can write that setting to an imported key, which you could reread instead of, running the whole simulation. Once it's run, for me, you actually write it into this, and then you could load that back up, so you don't have to rerun the simulation every time. So you run it once, and then, if you want to go and reinvestigate anything in a later time, you just reopen that that view here, which has all the data once it ran it. We're setting up the SPICE engine we're using, some thermal environment that needs to be set up, the substrate thickness, the extraction corner that we're going to be using, conductivity of different material in this section. There's the IR drop environment setup. So in order to know, okay, I'm dropping like 13 kilovolt, we need to have an exact location of where that VSS will drop on the die. So basically we're specifying critical voltage source, it's a VSS, and its exact location is those in it's on metal 1. And then I tell it it's a voltage 0, and that voltage source has 0 resistance internally. I do the same thing for the VDD here with its station on metal 1, and I'm telling it it's 1.1 volts. That's what I'm using as voltage. And then here I tell it the analysis that I'm going to be running, a transient. The corner is the single EC, and the type of analysis that's going to be done. So we're going to do thermal, power, and IR drop, and it's transient. So that is kind of it as far as the setting is concerned. Let's run it and play with that and see how much fun we can get. Okay, let's see. LS, make sure I'm at the right place. Okay, so you just InVar and click on that flow.tick file, that is the setup file. And I'm just going to run this. Opens the GUI, runs the simulation it needs to be running, so we kind of need to wait for that initial run to go through before we can actually go and inspect any aspect of the thermal or IR drop or anything like that. So recall we're running a transient of about 2 nanoseconds. It completed. So now say, okay, open the GUI. Okay, just say start. Well, no, they changed that. So you just use that red icon here, which opens the GUI. It goes and open the GDS. That's a really simple circuit. Looking actually forward to play with your redesign there and kind of see what you can get. So so this is a GDS. Now you can say display control. And this display control here shows up. So you have layout, which will allow you to basically say, okay, I want to see, click apply, then I see the contact. It's kind of my layer bar in Expert or in Tanner or whatever. Right? It allows you to set what layer and layout you want to see. Now, if I do everything, it looks pretty crowded. So you can set the opacity, basically, to apply, and then it's kind of transparent. It's staple, right? So if I turn off a few, I'm not interested. All the layer, apply, then I have my poly, I have my contact, and my metal one that I show right now. If I do F, it sends it goes like the full screen. If I click here and I type C, it centers that circuit. You can move left, move up, move down with the arrow. By pressing I or O, it's in and out. You come and say add to that area. Boom, it zooms in there, right? So a little shortcut to kind of help navigating through the layout. Okay, just the look and feel of the base layout wise. Now I go to the tab Map. This is where you have thermal, power, and metallization. So let's do thermal, for example. Okay, so we ran a transient Now the opacity is set to 1, which is 4, so let's say 0.2. And it's telling me that the range of temperature at any time during that 2 nanosecond goes from 25 to 25.03, almost no variation. Now you can come and say, okay, let me see that. Let me see which area gets hot, basically. So I can just play that, and as the simulation run, you can see in this little circuit area, those are the hot spots on that circuit. So you can see it's going green or more red. So it just eats up and it shows you live, basically during the simulation, winning, thermal-wise. See if you have a huge simulation. That may take a little bit of time. I mean, just kind of look at your hotspot. I would start with the static, which gives you the worst case, and then you're like, okay, well, I know it's this part of the circuit that gets really hot. Now, why and where in the simulation? Then you can maybe down. Okay, let's run it from this point to this point and see if it's in that area. Why is it getting so hot or something? Runs through like this, right? Now, an interesting aspect is that you can, with this one here, basically set up the GUI and say, I want to enable spatial search. What that does, it will allow you to click on a device, for example, this guy here, and then you say, I want to see your property. And it opens that little window here. And blow this up a little bit. So it's DNMOS, its orientation is 0, the exact position in the die, its temperature is 25.0079, and their information, dynamic power, and all of this. Now,
Michelle, sorry for interrupt. So that property is the current time property or a max property?
This one here is probably max that it reach across. We'll double check that, but I think it is. But let's double check that for that point. So here's where this comes in. You could say, I want to spec this point a little closer, so you can open that selection step and just add that device to the selection, and you say, show me the simulation chart of this guy. So otherwise, that would behaves across the 2 nanosecond. Otherwise, that's how it behaves across the 2 nanosecond. That for any device in circuit. So according to this, 5.0079, but we have like 5.02. No, it actually goes higher than that. So that's not the max. It goes higher than 0.02 here. That's not the max. Let me take a note here of what it really means, because I don't know, to be honest with you.
Okay, thank you.
Yep, no problem. 2. That's good.
Yep. To be a devil's advocate, do you have the schematic so we can see what the circuits are really doing?
No, I don't.
Oh.
No, I don't.
I think it's in flip-flop. We had a reset, I think. So
Get that? Sorry?
This cell is scan flip-flop cell. Has a clock, scan in, scan out, reset.
I'm gonna mess with Michelle and have them change the edge rate or have them do something to burn power, but
Yeah.
that's all right.
Yeah, we would have to go and change that GPS, change all of that. So I can't close the loop on that. We could sort of do that on your real test case, though.
I got another test case.
Michelle,
Pardon me?
I have one question. At the right, that object browser, it should M5 and there's a bar, time bar in there. Is it M5 is a cell or just one position of a cell?
M5 is actually, if I'm mistaken, this transfer that I clicked on, that's the name of that device in the net list.
Okay, that's a whole transistor. That's a whole transistor, not the position of a transistor.
Whole transistor.
Whole transistor.
I can't for sure, and that's something I need to double check with the other EE. But
Can you zoom in that layout view? In that area, and then turn the temperature, and can you do a cross section?
Oh.
Okay.
That's but this is transient. We will need to look at it, which we'll do after, which will show you the worst case.
Could you move time bar? Yeah, there's a bar in there. You can move that. Yeah, that one. That temperature changes.
It does.
Oh, it does. Yeah. Okay.
Yeah. So across. Okay. So the 79 is the ending point because right now I'm here. Yeah. Good catch.
Yeah.
Yeah. So it's the max, but you actually look at it. I don't know what all those warnings means. Time point using get time point. Something you like. But yeah, so you can send across. And I want to show you, but I'm just not on this and say I wanted to look at the source, but I wasn't really successful in doing this. So you have motivation when I was looking at that view. But seems like you could go and look into more details than just, M5.
Yeah, M5 is a multi-finger, big device that you want to see the temperature gradient.
Okay. Let me do that as well. M5 in object browser. All right, so let me close that for now. And a power is actually similar. You back up. Again, now it's like opaque, really opaque. So if it tells me across that simulation, I go from 0 to, 35 to 57 microwatt per square micron, and then you wouldn't see similarly. Whoops. If you again kind of the hot, where you consume power. across that simulation. So it's to the thermal as far as like how to play with the GUI there. And in the same way as we saw, you can look at chart across the simulation of power and thermal. So that's just what was printed basically there. So we got that. Right, so let's look at IR drop. Click this. It's up. The R drop that we set up, basically we say, okay, I want to see VSS and VDD. So I look at, for example, metal 1, and let's just look at VD to start. So if I just do a change, so has from 0 to 562.4 millivolt of drop, it looks like. Let me see.
Welcome. Yeah.
It seems to be staying to a purplish. Go ahead, sorry.
So, Richard Jensen, I just interrupted David.
No, I thought there was a question. Is there a question, or should I?
Oh, we were looking, and you just explained to us a little bit about what you're doing. Are you on this call? Tom?
Yeah, Thomas.
I am. I was muted.
Mr. Tammon? Can you break away and give me a call in my office real quick? I got something I need to run by you.
Okay.
A call from a customer, and I need to share something with you. In fact, take about 2 minutes.
So, transient, so we can. That. Now looking at both SS and VDD across that simulation span.
So your voltage source, can you share?
Source R? Yeah. Let me stop that. Let me bring that back up. For the VSS net, it was like 2279.13, right?
Mm-hmm.
So, if I'm mistaken, it is somewhere around here, 2279 and minus 13. Way to put it in, I just don't. They'd be somewhere around here, 22.9. So your VSS pin is kind of here, where the VD is more in this area. If we again add that file, the VDD was 11.7C2 and 14.19. So if you look in the bottom corner here, you see the coordinate. 2 and 14.19, roughly here for VDD.
Oh, Michelle, how the power line and the ground metal line has segmented? What's the rule?
If I didn't get the question, sorry?
Oh, okay. There's the voltage drop gradient from VDD to VSS. How do you divide those metal lines? How you segment it? I mean, whole metal line it has been divided in the certain, right?
Yeah.
And what is the rule?
Look only. Let me show you. Terrific. That reading the DSPF file and placing those parasitic resistance on those pieces of metal.
Okay.
How?
Is rectangular the same potential?
I would think so. Yeah. for like a little section.
Yeah.
Look at it. It's going to be here to see. Well, let's play it. Let's play
Yes,
it.
play, yeah. Okay.
Yeah, but it has a bit of. I'll get a little slower. Hold on. And that we'll be able to see more. So, okay. So let's put that to 400, for example. And go back to the IR drop. Yes, okay. Play. It seems like it has resolution. I can see some breakdown there, a little slit of color. And how the DSPF is precise or accurate as far as the down of location and value of resistor. It's just going to use directly the DSPF information. So let's stop now. It might be interesting to look at it on the stack side, which we'll run after. I turn this off for now. Alrighty. You can do that for both. You can do that for poly contact, whatever layer you have in the IR drop. Yeah, it's going to be on the static side. So let's go look at the static in this case. So I'm going to have to close this one. Exit. And let's open it. There's another tickle file that got set up. Similar setup. We're reading the GDS, the same layer map, reading the EM rule type of circuit. We're putting in file. The only thing here we're telling it that we're going to run a static analysis. And here also we're looking at, okay, it's going to be static. Power thermal IR drop supply electroration and single electromigration. So let's run it. What? Okay.
I say that quite a bit.
So, underscore static. Okay. Running through that simulation, then on complete, we'll be able to inspect the data.
So now, does this tool it basically extract the net list? Does it extract the net list based on layout, or do you have to give it additional data as it extracts squares for the IR drop, for instance?
The tool itself there does not perform any extraction. You need from expert to run a netlist extraction and provide the DSPF as well. So you have the parasitic, information of the circuit that's along with the GDS. Does that answer the question?
In a way. So we're looking at, you get a point to start from, it's looking at, there you said DSPS, that's process information about per square, et cetera. It looks at relative placement to the active node back to the origin of the power or whatever.
Correct. Yeah, correct.
Okay.
So if we look at basically needs this file, which this net SE is here, and connect to all those instances at those locations, and then we have capacitance, on this node, and we have some resistance at X and Y location, and basically here's a breakdown, for example, of a resistor. So for the same Y of 1.067, it has a 0.102 to 0.195. So that's a little resistor there. And so that's what it uses to determine which should be colored, which color, basically, in terms of thermal or power and all of this. So that's the brain of those coordinates. So run this static. So it brings the same GDS, that's the same circuit. If I bring the display control, and this time turn on, these three again, and turn up a yellow light. Apply, okay. And then we look at thermal. Now different. Basically shows me the range of temperature that it's going to get root 26 to 26.28, where our warmest point. So there, right there, basically those transistors here are the warmest. If we look at emitting resistor surge, similarly, if I click on this guy, property, the highest that this point gets, basically, with that location, or that is dissipated through it. Is similar in a way. It's again, kind of the worst case. Then if we go to IR drop, put that on. Okay. So let me. Okay. So 0 to 147. Okay. Let me turn up the layout a little bit. Keep metal 1. And put that to 0.2. Okay. IR drop. Metal 1.
Michelle, is there a way, when you say static, you relate to temperature, power, or IR drop? Is that an option? When it's either max power, kind of that snapshot, right?
It
Or a
basically
snapshot of temperature, max temperature, and then capture the IR and power that instant. Always the max, higher max, because they happen at different times.
right. Yeah. I'm not 100% sure, Dave. So I'll double check on that. I don't want to lie to you. So let me write this down. got this down. So the interesting thing here, if you click enable, it's already enabled. But you can come and click here. It gives you the exact value at that point. I come and click here, and it gives me the exact value. So it's VDD, and the voltage is 953, and the reference is 1.1. Voltage drop for that at that point is roughly 100 millivolts, right? Whereas here, if you go closer to where it is, you only have like 51 millivolts of drop. Yeah.
On the poly and see what the poly drop is.
Okay. Let me see here. On poly. Yeah. Applied range. It doesn't seem to be showing it. Stopping at the device there.
It's only to metal one. I'm assuming the white boxes are poly.
Yeah. Really.
Okay.
Yeah. It's the purple is actually poly. If I'm into this, yeah. Yeah, so the poly, metal one, apply. So here seems to be connecting, but it doesn't seem to have any IR change on the poly itself.
Well, from a static perspective or a static simulation, probably wouldn't.
Correct. Yep.
I thought IR would be at the active area rather than the poly.
I think that.
The gate. The source would be the one of the well, the active rather than the poly itself.
A lot of feedback going on. It's hard to understand. Or the D-Day.
Let's keep going. I'm sure I'm put together a list of unanswered questions, and that I have to get back to you on. And when we follow up, we could spend time maybe on that example and look at your other circuits. So basically, you can click and see the voltage. You could also say report voltage node, and hold on. And it gives you a list. 1, 2, 3, 4, 5, about 10 of the biggest offender. And I think it's set up. I don't recall exactly what you set it up, but you can get more. And then you can basically click on this one, and it's going to show you exactly where that is in the circuit. Click on this one, it shows you where it's at. Okay. I can play with that range. Say I want manual range instead of one. I wanted it to 250. Okay. And then obviously your color changes a little. Oh, you remove the auto range, and I want to set 200.
has meeting.
So, I mean, obviously your color scheme will change, but usually auto range does a pretty good job at giving you the span of what is here. Electron migration will show you the current density on your line. Similarly, if you click here, it gives you the current average current density at that spot. So you have your worst offender in this area, or it can make sense around your VDD. You know, there's a lot of, you know, from that pad basically. And here it's purple because it doesn't drive anything. So I'm going to show you that. And you have this single net as well. Hold on, single net. Analog, yeah. Okay. Analog net will change shortly. It's going to be all single net. That's going to be changed to GUI, but then it extends it to the in the circuit on metal 1, the current density, so you can see how it is in the circuit. You could look at it with the contact, or you know, just a contact, or your biggest current. And from earlier simulation, when we were running the transient, we remember that this area was basically where there was a lot of power consumption and high temperature. So it makes sense that the current density at those points may go higher.
I remember earlier you enter electromigration rules. So if anywhere in the circuit it violates the rule, how do you just have those areas? So showing where it violated the rules.
And let me see. Range. You can say I don't care about anything under 5. And show me only whatever above 6. Apply. So then you get your span above 6. So that one way, you know, if you're like, no, I don't even want to see above 6. I want to see above 6.9, and then I change. Seem to apply. Hold on. Oh, okay. I'm on the. Yeah, that's what I want to see. Here, I'm on the single net still. So range. That's electromigration. Okay, if one is 0.7 and above, apply. Then I would see, you know, everything else is purple. So that would be your hotspot. Your
Okay.
That'd be the way to around that. I don't know what I had.
I'm sitting here going, see, in a large device, I could see a really good example tool and something like that, if you ever thought about it. In other words, the eye drop of the metal that, let's just say you had a really wide transistor, you look at what the maximum width of the transistor would be that you'd want to kind of about IR drop across the poly, how much metal drop you have from, say, the center of the transistor to the back edge, or say the far edge of a source to the metal butt. I could see some really good applications for this in something like that.
I'll have to talk to our AE about this, because at the moment, because it kind of reads the DSPF, it considers the device as a sort of black box, right? It's kind of it's lost, but then and then the model will take care of that. So it only considers the routing getting to the device, the routing parasitic. I'll talk to him about like in a situation like that where you look at a given device and kind of stopping at the device itself, not only stopping at the boundary.
Yeah, I can definitely see that. You'd have to, put, say, files in parallel transistors or something and have it start analyzing the device from that perspective. But, so right. I'm assuming it's kind of how you set it up. Question throughout with me is, how big of a transistor do you need versus how many fingers, et cetera, from a power device perspective? Is a question for me.
So at this moment, I can't give you a firm answer on this, but I will follow up.
So for our drop, we can only see the metal, contact, and poly. Can we see the distribution?
Well, I think it depends on. Hold on, let me put this up here. This, okay. It depends on what's specified here. So we specify contact, poly, and metal, right? So if you add more information about the process stack, then probably you could go into other layer. This moment in this example, it's not provided, so it kind of stops there, right? And because we're looking at a DSPF for location of the parasitic device and all of that, and it's only so they consider routing as the metal one, the poly, the contact. That ties in some ways in the question that was just asked in a way, how can more device and not only the routing that is surrounding all of this.
It's going to be very similar to the next example too. So.
Yeah.
I have a question about the simulation that you were running, the 2 nanosecond simulation versus the static simulation. Do you need to provide some kind of stimulus input of?
Yes. For example, here I had a clock at a frequency. They had the D switching at another frequency.
Static.
So you need to provide. Pardon me?
Is this a static simulation?
This was actually what we used for the transient there.
Oh, okay.
This as your input deck. You'll be able to run that simulation in Smart Spice.
Okay.
What it does, it basically calls Smart Spice and run it. Next step for me, in order to work with your other example that you provided, your DEI chip, you need to look at the input deck or just the net that I got and the stimulus and make sure that this run in Smart Spice. That's always kind of my first level of verification. If it doesn't work, then we have a problem. And then set it up so it could be used by InVar. So basically set up all those ITF map file and all of this so we can basically do a similar demonstration using your real data. Sorry.
Okay. So
kind
prepare for our specific design examples. Are you thinking, so can we maybe reconvene in about a week, or?
I think in a week would be good. I think that would give me plenty of time to prepare that.
Okay.
During that week.
Thursday, 1:30 p.m.
That's that. Yes.
Okay. My list here, we want to look at the transistor final resolution, maybe possibly source and drain. And the second item is we want to check the in the scheme mode how can make a different snapshot criteria. And the third is how do we for the IR drop on the poly. And then the fourth one is if we have our device application, how can we see individual temperature distribution?
Okay. So I'm going to put that into kind of an action item list. Let me go through my note here, make sure we're on the same page there. Okay, there's like when we actually look at the M5 device, that kind of ties into what you just mentioned, but like have bigger resolution as far as temperature or power consumption for the drain, the gate, the source, having a bigger breakdown than just like 5. Yeah, and I think the other one you captured. So.
Okay.
Yeah, it's kind of what I had today as a first demo on this. Do you have any other questions at this point that may or may not be able to answer right away? But shoot, if you have any other.
If you have any more questions, send you an email.
Okay. So during the week, as I prepared for this next one, would you be my main point of contact, David? If I question on what was provided in all of this?
Yeah.
Okay.
Just pound.
I'll keep you as the main person, and then you can reroute. But sure. Okay, so let me get going then on that other data, and we'll talk during the week.
Sounds great.
So I was wondering if you really capture that video, if that'd be share with me, also. Keep it for instance. But
it's to download a WebEx application, then you can view it. It's a proprietary format.
I do have web.
Oh, yeah.
I do have.
You can send me the FTP link. I can upload it.
Okay. So if there's not any other question, we'll just today, and then we'll talk in a week or so.
Yep.
Thank you.
Thank you.
All right.
Okay.